So this is some background about the second part. In other words, how do you predict from an upfield here above your acquisition? What was that all about? You understand? And then Jingwu will actually show what she did. So there's 4 reasons that we're interested in traditional wave prediction and migration in the group. 4 reasons. One is it's an ingredient, as you're about to see, in a wave separation method for data on a non-horizontal measurement surface. Right? That's Jingwu's contribution. Yes? In other words, that is motivating me saying some words about it right now. We have an interest in capable multi-directional migration because we need a migration to provide a definitive response to the question multiple signal or noise. And I'll give a talk on that later. Yes? And then, in other words, if we're saying you have to remove multiples, yes? Why do you need to remove multiples? Yes? Let's ask and answer that question. Yes? You need a migration that's capable of dealing with primaries and multiples. Yes? So that's an interest. We want to, this is sort of an accidental project. We came to be aware that you can produce a migration, the first migration, that's equally effective at all frequencies at the target and reservoir. And we'll have some words to say about that. You have to say more than a few words. If you say it's the first migration method that's equally effective at the reservoir, you've got to say why all current migrations aren't. You can't just say it, you've got to show it, yes? So we show that, yes? And then that's a surprise to a lot of people. If you say Kirchhoff is asymptotic, if you say RTM is asymptotic, yes? A lot of people get upset. Look how much money we're spending on HPC. You're telling me we made a high frequency approximation? What's next? You know? So we'll show that, okay? It's the imaging principle that it's right at the beginning, its origin is a high frequency approximation. And then there's an ingredient within our multiple attenuation and elimination internal multiple that involves an imaging, a water speed imaging. So these are the reasons so that so wave theory methods for migration have 2 components: some wave propagation idea and an imaging principle. And the imaging principles, to pick an important reference, we picked John Claerbout's 1971 paper. We've called these labels Claerbout I, II, III. This is our labels, okay? That doesn't mean he invented these, yes? They're in his paper. The exploding reflector model is Dan Lowenthal, yes? That's for 0 offset data. It says that if you have a 0 offset experiment and there's a symmetry, in other words, it goes back and then forth in ray theory to that, yes? So there's the path to the reflector and the path back is on the same line, the same ray, so that if instead of saying it went from the source to the reflector and back to the receiver, you say, so the 0 time is when the source went off, then T/2 to the reflector, and then another T/2 to the receiver. So the idea of Lowenthal was, instead of doing that, you're not interested in locating the source, you're interested in locating the reflector. So go back with half the velocity and ask for T=0, okay? Because the full velocity T=0, you'll find the source, okay? Half the velocity at, yes, with T=0, you'll locate the reflector. That's so then at T=0 with that picture, the reflector exploded. That's where exploding reflector, okay? That's only for 0 offset. Claerbout II and III are for, these are the imaging principles, are for pre-stack. The second one says, take your reflection data back. Take your, and I'll explain what I mean by back. That's critical. And take the source field forward. Take the reflection data back, take the source field forward, and find where they are time and space coincident. This time and space coincident of the recorded data back and the source field forward is the location of an image. Yes? That's the principle. What it was meant initially was back in depth. Go back in depth and go forward in depth with the source field. Okay? And that was for one-way waves. 1983, Whitmore, George McMechen, Hongbo, yes? Yes, the reverse time migration came from Claerbout II. The same idea, except don't go back in depth. Don't take the data back in depth. Take it back in time, yes? And take the source field forward in time. The difference between time and depth is not anything for one-way waves. Of course, for one-way waves, deeper and larger time, it's monotonic, yes? But the whole idea was they were looking for diving waves, yes? Which could increase time, but depth would go higher and then lower, yes? So they wanted back in time, forward in time, and then time-space coincident. That is the current Claerbout II, with a big further contribution, advance. Yu Zhang, Sheng Zhu, Bleistein added another, I probably left some people off. They said, in addition to bring back in time and, yes, and forward in time the source, make an assumption that the reflection data is a geometric optics multiply times the source field. That what comes up is R times what went down. That R times incident is up. Understood? Okay, so that's Claerbout II with its extensions, yes? Into time and into R, yes? Geometric optics. Claerbout III is a different principle. I'm going to say how it initially was and then how it evolved. That idea is you predict from actual sources and receivers what would a source and receiver do at depth, yes? Once you have a source and receiver at depth, then you say make the source and receiver that you predict coincident initially, and then ask for small positive time, yes? If you're far from a reflector, it's going to take a non-zero time. If you ask what is the zero time component when you're far from a reflector, the answer is 0. When you're right above a reflector, you get a non-zero, yes? You get a definitive yes or no at every point in the subsurface with Claerbout III. You have a source and receiver, coincident, you ask for t equals 0, the answer is you get an amplitude or nothing. Amplitude means there's structure right there. No candidates, no travel time curves, okay? So this initial idea got extended by Stolt and colleagues. That initial idea was relaxed to not be only X coincident, give it a slight ability to move, XH not 0, and examine it, and you're going to get amplitude information, keep the KH information. In addition, Stolt introduced, as soon as he did that, you got a plane wave reflection coefficient, okay? Not geometric optics, plane wave, you're in Fourier. And then one further step from inverse scattering, he set that equal to G0, V1, G0, which gave him the ability to take Claerbout III into amplitude and an ability to image specular when there is specular. Well, as soon as you have a curved boundary, a plane wave doesn't produce a plane wave, okay? When you have a pinch out, a plane wave doesn't produce a So there's a model that's Stolt has called point reflectivity that extended the original Claerbout III. We call this Stolt extended Claerbout III means two things. Get the amplitude information by keeping KH information. You'll see detail about it. And then also put a point reflectivity that if you have specular, will give you a reflection coefficient automatically. And if you don't, will give you a different function, which for an incident plane wave will give you a spread of wave numbers, yes? Automatically. So if you have specular, one plane wave will give you one plane wave about a normal, yes, to that, yes? And so that, that extension, those extensions are not possible in two, okay?
So far?
Yes.
Since you're concerned about correctly handling different frequencies here, this doesn't embody any sort of Q effects, which I would think at some point become pretty important when you're trying to handle the frequencies.
Extremely important. So that's what we do is we're going to isolate the issue of the imaging principle when you'll see comparisons from implementing. In other words, if I'm going to do Claerbout III through absorption, and I'm going to suffer. Because, in other words, you're going to lose, okay? Well, the question is, in other words, there are two issues. One is, what is your imaging principle? So you'll see tests where it's homogeneous. Homogeneous, no absorption. Just look at the principle, yes? So then it's not an issue of absorption or how you implement it. So how you implement, which we'll discuss, what we have added is how to implement, not the imaging principle. So what we're doing in our group now is analogous to what Whitmore and McMecken, Hungbo did, where they allowed two-way time, two-way propagation. In other words, the Claerbout III, extended by Stolt, up to now is for one-way waves. We wanted this, so there's a talk that I'm going to give later prior to those comparisons. This is a very limited thing to help to set up Jingwu, where I say, how do you know a migration, how can you tell a migration is made a high frequency approximation? One is, look at the imaging principle itself, where you don't have any issues about how you implemented it. You just did it perfectly, where there's no absorption, there's no velocity issue. So I'll give an example. If we're going to predict the source and receiver, if we assume, if it's a homogeneous medium, okay, for a second, then waves at every point travel in one direction, down, in homogeneous. Any deviation from homogeneous, like when you say two-way wave and you do this, at every point you assume the wave is moving in one direction. At every point, overall it moved in two, down and up. But if you are assuming a medium which is not homogeneous, and you're assuming that at every point it's moving in one direction, that's a high frequency approximation. So every issue like that we're avoiding. We're going to do our best for, given whatever velocity absorption you have, to not let the implementation and the principle bring in a high frequency approximation. So we're not saying we're going to be effective. The words are very carefully chosen. We're going to be equally effective at all frequencies. We might be totally ineffective at every frequency, but we'll be equally ineffective at every frequency. No, that's a very important point because that's to your point. How am I going to deal with absorption, yes? I'm saying whatever you're doing, yes? The words are the first migration method that's equally effective at each frequency. Doesn't mean any one of them is effective, okay? But we're not going to be prejudicing we're not going to be more effective, whatever effective means, yes, on the high end and the low, and you'll see results. You'll see resolution results of this versus this. In other words, there are ways of indicating with resolution what happened. As I mentioned earlier, we got reports from companies that they're spending money on lower frequency, and they see it in the data, but not in the migration. We had last year looked at some results with imaging that indicated that our RTM is high frequency. Yes, so we said, wow, they're implementing something, and Stolt said that's right. They're damaging. In the principle itself is damaging low frequency. So it doesn't matter if you pay for more, you're not treating it well. This guy doesn't. You'll see. We'll examine. So how do you know? If anywhere in your migration, you see a travel time curve. If anywhere in your migration, any step, you see a travel time curve, that's a high frequency approximation. Why? A travel time curve is, you give me, here's a source and receiver, a time, something arose, right? Some event came. And I put it on an ellipse in my grip. If you put it on an ellipse, yes, in your migration, you get some t equals r over c, yes, and you put it on a curve. Think what that curve is. It's a curve of candidates, yes, of possible xz's, such that they satisfy this plus this is the time. That's ray theory. When you do this, there's no candidates at a point xz, yes or no. This gives you candidates, yes. You'll see it, okay? It's done. This is not what my talk was supposed to be. But when you asked about absorption, you got me off in another world. So the point is, we're not saying that we're going to be. All we're saying is we're going to equally maltreat every frequency, or equally well treat every frequency, but we're not going to prejudice towards high frequency, okay? So we still might be totally ineffective, but we're not going to be less effective on the low end. Is that clear? The word equally effective does not mean effective anywhere. That's a truth. I'm being straight. It's because your question, of course, biased, and you'll see the results of it in terms of resolving, later in this meeting. The differences between this and this, where each gets more low frequency, and what difference does it make? This makes a lot more difference than that. Yes, that's what we mean at the target. Yes, not in the data. The data, in both cases, are the same. So you see the advantage in the data. You don't see the same advantage. It's not that one has no advantage with low frequency. It's just that this has more advantage, better resolution. Yes. Okay. Anyway, that's not what I was supposed to be saying right now.
Well, it's a link between attenuation and dispersion.
There you go.
When you got your absorption.
Yes. Well, you'll see tomorrow. This is all traditional. Yes. This talk, SEP could follow maybe. Tomorrow, not. When you do ISS imaging, you just went outside the volume, so to speak. The volume. Okay. I just said all this. Don't worry about it. Okay. This is the part I was supposed to say. So this is, we talked about earlier, yes? Some kind of model, and we talked about that, and we talked about this. And we talked about this. And this was for wave separation. Why wave separation? We wanted to hook this up with being the contribution due to sources outside the volume. So you needed a G0 plus. But if I'm interested in wave prediction, this is if I don't care about separating, in other words, this guy is the portion, this is the contribution due to sources outside the volume. I need plus, because this is the contribution with rho G0 plus due to sources in. So if I want this to be the contribution due to sources out, I must make plus. But if I don't have that interest anymore, that's wave separation. The portion of a wave due to something, yes? Right now, we're not in wave separation anymore. I'm in now wave prediction. Of course, I'm going to do Claerbout III, you understand? For prediction, I want this. For that, I'm not interested in comparing this to any G0 plus thing. I just want to predict. Any G0 will work here for this, okay? So, okay, so the point is, what we're going to assume in migration theory, here's the key, again, to Jim, your question, is this row here will have two things. We'll have that A of omega, or is that row that was in that integral. We'll have this, and we'll have this, yes? Let's assume, as with all traditional migration, that where we're migrating, we know the velocity, yes? In other words, that C0 is the velocity, yes? Not everywhere, only where people criticize, nobody here is older enough to remember this, I do. When I first entered oil, Claerbout was a radical. And he was criticized. I'll show you examples why. Because, you need the velocity to get with wave migration. Where I worked, there were 3 papers in February '78 geophysics. There was Stolt, Schneider, and one other. The one other was where I worked and didn't believe in wave theory anything. Okay? You understand? So I heard wave theory is no panacea. You know, Claerbout was radical in 1980. I know it's hard for you to believe now, yes? So after he was a success, Chevron said he was a consultant here. But they considered him radical when he was a consultant there, you know? So the point being, the migration doesn't assume you know the velocity everywhere. It assumes you know the velocity enough to find a reflector. You don't need to know it below. So but within the volume where you're trying to predict a field, you're going to assume that this is the velocity. It doesn't have to be a constant, some reference. Yes. So this is 0. Yes. And the source will be outside where you're going to, the source is not where you're trying to predict. So the point is that the rho in the volume is 0 in migration. And so that in this predictor here, in traditional migration, rho is 0. When you do the inverse scattering series, that's where they change path. You say, I don't know it. I want to find a field inside the volume, and I don't know the velocity. So you can't make that 0. You understand? Then you get the forward scattering series, the inverse scattering series. It's right there at that juncture. Okay? So we're doing traditional migration here, where we assume within the region that we want to predict the field, we know information. Yes? By the way, migration is a direct inverse. You give me the velocity, it gives you the depth. It doesn't search, it doesn't match. Yes? It's a linear and direct inverse. you have the right velocity, you have the right depth. You do Claerbout III, you find structure. Of course, you hear me talk a lot about direct. That is direct. Yes. So the point is, you have P equals an integral, and it doesn't have to be G0 plus to predict inside. So here's, see, this in 1978, this was the model. If you look at Schneider's paper, Schneider, February 1978, Geophysics, the same, what a journal, that Stolt migration and Schneider migration in one edition, yes? And they refer to each other in the appendices. They show they were equivalent. Amazing. So, but that's what the model was. And it was brought under tremendous criticism. You're telling me you need to know the whole world and then you're going to tell me the world? Wow. You know? You understand? I remember hearing all this. So it turns out that there are issues here. There are issues here besides the fact that there's nothing unknown. In other words, it's assumed the whole world is known. Yes? There are other issues that when you use some anti-causal Green's function, it doesn't go away the contribution down here. It's not Sommerfeld. Anyway, this evolved to this, okay? Where, and this is the current migration model, where there's some volume to some finite depth that you know. And below that you don't know and you don't need to know, yes? And you're going to do a surface integral around that part that you assume you know the information to predict the field in here to do Claerbout III. First get the receiver predicted and the source predicted, yes? So Stolt also talked about approximately known. Inverse scattering series says everything's unknown. There's no piece of the volume that's known. You're just going to do everything directly in terms of unknown. That's what we'll talk about tomorrow, okay? We're taking you slowly to that. You see? We don't want to break it to you all at once. So, including imaging, you'll see, yes? It's important for you to see the inverse scattering, as I said earlier today, when it arrives, and you'll see where it is and what it yet needs to do, it's going to change seismic processing. That, there's no doubt. When you see the results on Mamusi and field data, to date, yes, and fast, lightning fast, faster than our multiple methods for sure, yes, then when you see the intelligence in it, you will understand that the thing that will be a sea change in imaging is not our Stolt extended Claerbout III for heterogeneous. That's going to add some value, you understand? It's not going to change that deep water drill success rate, that needle, you know, by a lot. Okay, so the point is that upper right is the model, yes? Okay, so the upper right is, now this is the upper right model, yes, that piece and some unknown down here. So you have an upper surface, a lower surface. The question is, okay, so you didn't make this go to infinity, but you don't have measurements down here. Yes? You don't have measurements. You only have measurements on the top. How are you going to predict? So you can show, and that's the point, that if you have a wave that moves up, that you're trying to predict from measurements that are on here of a wave that's moving up in this volume and measured and it's up, and you're trying to predict it in here, if you pick an anti-causal Green's function, yes, that the contribution from the lower surface will be zero. It won't contribute. You can show that analytically. And so the upper surface is all you need to predict an up wave. And if you, and that becomes Stolt migration. Okay? Why? The reason is this. If you have measurements on top and anti-causal, it tells you what a wave was in the past. Anti-causal, yes? When it's moving up, from here, anti-causal tells you where it was. If I picked here G0 plus, it would only need this and not that for a wave moving this way. In other words, G0 plus will predict the future of these waves here, understand? Which will be up. But since they're up here, our measurements and the wave we're trying to predict is like that, anti-causal. If you put anti-causal into Green's theorem, you get Stolt migration, okay? So that's the story. And that's what it looks like. Pre-stack Stolt migration and blah, 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 all that, how Stolt migration works. So this is to provide some background to the landmark work of Jing Wu, yes, who's using a form of prediction which is in Claerbout III to arrange to do wave separation methods on your actual measurements when your measurement surface is not horizontal. Understood? So she's going to do it's going to be two steps. One is the normal, make it separated above, and then she takes the above, which are going up, and does a G0 minus to bring them in, yes? With that same kind of surface. So it's a two-step thing, which will now allow you to do your wave separation on your data, and ExxonMobil will be happy, yes? Okay. Now, up to before Jing Wu, that was only possible for horizontal with K omega. Okay, Jing Wu, it's all yours.